Welcome students to the part 2 of this chapter, Work and Energy, from class 9 of physics. The first part of the chapter you will get in the playlist of class 9. It is given there with the thumbnail, Work and Energy part 1. Okay, so let's start. Before this, in the part 1 we have studied about work, isn't it? So now we will study about the energy. So let's start here. So energy is what? Actually, by the picture what we can say, what is it actually? This is obviously a solar energy, isn't it? From sun we capture the energy and in the solar panels. So here what is said, an object having a capability to do work is said to possess energy. Means if a person is doing some work, if a person is moving on a staircase to move from the ground floor to a second floor building, okay, so he is doing some work, but he also needs some energy. Can a ill person move very faster from a ground floor to the second floor? Can a ill person move, or he will use the elevator, isn't it? But a very active person, means who have the most energy, he can move very easily by running or by walking, okay, from ground floor to the second floor. This is just an example. So see here, the object which does the work loses energy and the object on which the work is done gains energy. This point please keep it noted. The object which does the work means the person is doing the work, it will lose the energy. Like a person is kicking a ball, okay, he is kicking a ball, so he will lose the energy. Means he has run one football match is there, he has run and he has kicked the ball, okay, so little bit of energy is lost from his body. And the object on which the work is done, means on the ball the work is done, then what will happen? That will gain the energy and the ball will move very fast to the another player, isn't it? So this is the concept, that energy is what? An object that having the capability to do work is said to possess the energy, and the object which does the energy loses the energy, and the object on which the work is done, that will gain the energy. Clear? Now come to the next slide. How does an object with energy do work? Now let's see. An object that possesses energy can exert a force on another object. Just now we have taken the example of football player, isn't it? When this happens, energy is transferred from former to the later. Former means what? That football player. And later means what? That the ball. Okay. The second object may move as it receives energy and therefore it will do some work. As the ball will gain some energy, it will do, means it will move from one player to the another. Thus, the first object had the capacity to do work. Means the player has the capacity to do the work. The energy possessed by the object is thus measured in terms of its capacity of doing the work. The unit of energy is therefore the same as that of work. Means how much work done, we got joule, isn't it? Here also same energy. So 1 joule is what? The energy required to do 1 joule of work. Sometimes a larger unit of energy called the kilojoule is also used. So 1 kilojoule is how much? 1000 joule. Clear? So this is how from one body to another energy is transferred. Now we'll talk about some forms of energy. So let's start. There are some forms are given here. We have already studied before in previous classes, isn't it? So mechanical energy, we know that it is a combination of potential and kinetic energy. Heat energy we know about heat energy, that is the sun we get from that. Chemical energy, that is transferred from food to our body and we use that energy, isn't it? Electrical energy, like by electricity passing through the wire and a bulb is glowing, so that is electrical energy. Light energy, we get the light in us, or the sun gives us the energy, that is also the light energy, okay? So these are forms of energy, but here we will talk about mainly about kinetic and how to derive that kinetic energy, and we will talk about the potential energy, okay? So let's start. So see here, kinetic energy is what actually? Kinetic energy is the energy possessed by an object due to its motion. Whatever the motion will be there, that is the kinetic energy, and the kinetic energy of an object increases with its speed. How much it will increase the speed. Okay, kinetic energy of a body moving with a certain velocity is equal to the work done to make the acquired at velocity. So how much velocity you are doing, okay, so that object will acquire that same velocity. Like say here, examples are given of meteors. So meteors, when it falls down in our earth, so the earth will pull, isn't it? The gravitational force of our earth will pull the meteor to the surface of our earth. So at what speed it will come, or what velocity it will enter, the same velocity it will reach the surface also. Like walking, you're walking like you're having a walk in the morning time. Okay, so you're walking in one speed, you're having, it may increase also with its speed. Okay, now then falling, throwing a ball, flying airplane. So these are types of the energy, means that energy will be continuous. Like also you can see an example of falling coconut. Falling, when coconut is falling, that is a kinetic energy. Not before falling, when the coconut is already thrown, means already it is detached from the branch of the stack of the coconuts. So it is a falling coconut. A speeding car, a car is speeding, or then a rolling stone, a flying aircraft you have seen here, flowing water, blowing wind, running athlete. So these are some examples of the kinetic energy. So here I have shown only little bit. Okay, 5 examples I have shown here. Now we will derive this kinetic energy. Actually we have got before that kinetic energy K is equal to half mv square, but how to derive it? Let's see. Kinetic energy, let object of mass m moving with uniform velocity u. Okay, uniform velocity means just velocity, no initial, no final, nothing, just a uniform speed it is continuing, displaced through a distance s when a constant force F acts on the direction of displacement. So from this statement we get that W work done is equal to F into S. This is the first equation. Next, velocity change from U to V. Okay, then A with the acceleration. If velocity is changed, means final velocity is there, initial velocity is there, we know that acceleration is what? V minus U by T, we can find it. So if U to V we have to find it, then A will be there, means acceleration of the body will be there. So we know these 3 relations. Already we have studied this one in the motion. Okay, in your chapter motion you have studied this. So V is equal to U plus AT. S is equal, S means distance, equal to UT plus half AT square. Third one is twice AS is equal to V square minus U square. These relations are connecting initial velocity U and final velocity V with uniform acceleration A. Now from the third equation we will take V square minus U square equal to twice AS. Then S we will get, keep it separate, we will get V square minus U square divided by twice it. That is the second equation. Now we know that F is equal to MA. We know for force is equal to mass into acceleration. That is we have taken in the third equation. Okay, we have got 3 equations. First, W is equal to F into S. Number 2, what we have get equations 2, S equal to V square minus U square by twice A. Okay, and F we have get F is equal to MA, that is 3. Now we will put A 2 and 3 in number 1. Number 1 what we have F. So in F we will put MA. Then in S we will put what? This one, equation 2. So in simplifying this 2 we will get half M we will keep it separate, in bracket V square minus U square. Next, if object will start from the stationary position U is equal to 0, so what will happen? Then W is equal to half mv square. U is 0, we have taken the equation U is 0, see from the previous slide, U is 0, we have put there, means the stationary, it means at rest, the object it is at rest. Now work done is equal to the change in kinetic energy of the object. We know that in kinetic energy there is no initial velocity. It is continuing. The velocity is continuing. You're walking, you're going. There is no, it is not said that you have a displacement from this state to this state, isn't it? So you're continuing. So here U will be equal to 0. So work done equal to half mv square. Then work done means what? The kinetic energy. Thus the kinetic energy possessed by an object of mass m and moving with a uniform velocity v. Now here uniform velocity will be, this is continuous. Okay, kinetic energy is always continuous. That is equal to Ek. K will be in the suffix. Okay, Ek equal to half mv square. So this is the kinetic energy. We have derived it. Before we have got this in the previous classes, but now we have derived it also. See, we are so studious, isn't it? We have derived the kinetic energy also. Okay, so this, note it down, the whole how to derive that Ek is equal to half mv square. Just note it down from the previous slide. Clear? Now we'll talk about the potential energy. Let's see here. Potential energy possessed by the object is the energy present in it by virtue of its position or configuration. So here we will see that the object will, at that position, the energy, what energy is present there in that position. Okay, so the energy transferred to an object is stored as potential energy. We will store that energy there. See, first this you have seen it is stretched there, then it will release. But before releasing, you have stretched, no? So that potential energy is stored. The energy is stored there. How much force here means releasing? Like the bow and arrow, the small boy is capturing. What he will do? He will pull the arrow on his backside. Then he will release it. Means how much energy is storing there? That is the potential energy. Okay. And if it is not used to cause a change in velocity or speed of the object. So on the third, can you see there? One stone is about to fall from the peak of the hill or the plain. Okay. So before kinetic energy, how much potential energy is there? Kinetic energy, we got that it is continuous, but potential energy is always stored. Okay, it is always transferred to an object to store that potential energy. Okay, so now we will derive it. Let's see how. Potential energy of an object at a height. Now we'll talk about object from ground. We will take to one height. Okay, now see, work done in raising an object from the ground to that point against gravity is called the gravitational potential energy. Like you are playing with your brother or sister with a ball. You have to throw the ball from your hands. So what you will do? You will pick up the ball from the ground and you will take to your up, and then you will throw the ball to your sister. Okay, so you have done some work. You have raised the object from the ground to the point that it was against gravity, because what will do? Gravity will pull down, isn't it? So like here you see, here one mass m is raised through a height h from the ground. Now here force is required to do this. So the minimum force required to raise the object is equal to the weight of the object mg. Weight of the object we know, mass and gravitation. Okay, m into g. So the object gains energy equal to the work done on it. How much work is done? Force into displacement. Force is what? M into g, and displacement is how much height? H. So mg h. See, we got W is equal to mgh, means how much work done to do that type of work. Okay, what work we have got? Mgh. Since the work done on the object is equal to mgh and energy is equal to mgh units is gained by the object, and so this is potential energy is mgh, means before throwing the ball to your sister, you are holding the ball in your hands. How much work done you have done from the ground? mgh. Clear? So this is the potential energy. Now we'll talk about the law of conservation of energy. So let's start. Law of conservation of energy. When energy gets transformed, the total energy remains unchanged. Okay, when it's transformed, the energy will not change then. Okay, this is the law of conservation of energy. Note this down. According to this law, what is there? See, energy can only be converted from one form to another. It can neither be created nor destroyed. You cannot you cannot create an energy or cannot destroy an energy. If that object has energy, you can transform it from one position to another, from one form to another. Okay, total energy before and after transformation remains the same. So the law of conservation of energy is valid in all the situations and all kinds of transformation. Now let's see here. Law of conservation of energy. Here, let an object, okay, here object of mass, how much is taken? M. It is made to fall freely from the height h. Now, we got what? Potential energy mgh in one height. See here. In an object mass m, in the above what I have written there, that potential energy EP is equal to mgh, and their kinetic energy is 0 because it is not thrown, or that object m is not pulled down. Okay, so there no kinetic energy is there, but potential energy is there. So here kinetic energy is 0 because its velocity is 0 there. It is not moved. Okay. Now as it falls, potential energy will change to kinetic energy. Means EP will change to EK and E velocity is V. Now in the middle of C, in the height h, then EP will change to EK I have written. Why? Because here slowly what will happen? Slowly the kinetic energy will be greater, means it will start falling. The m mass object will start falling, so their kinetic energy will be more than the potential energy. Now before reaching the ground, means h equal to 0. See the arrow sign, capital H I have written, equal to 0. Here velocity will be highest. Okay, and EK means kinetic energy will be what? Highest, and potential energy will be lowest because it has started falling and before reaching the ground. In the ground it is not happen. Not in the ground. Before reaching the slightest point, before reaching the ground, what will happen? Kinetic energy will be greater than the potential energy. Now the sum of the kinetic energy and the potential energy would be the same, so it is a constant. So mgh plus half mv square is equal to constant. Therefore is what? The sum of kinetic energy and potential energy of an object is total to the mechanical energy. We have already in the forms of energy we have studied that this is a sum of kinetic and the potential energy. So this is the law of conservation of energy. From there we have studied that in mechanical energy these two energies is a sum of each other. Okay, now let's see another concept. Rate of doing work. Rate of doing work means what? Power measures the speed of the work done. How much power you have to change the speed of that work. Okay, it is defined as the rate of the doing work or rate of transfer of the energy. If an agent of work, the work W in time t, then power is given by power is equal to work by time means W by T. So SI unit of power is what? Watt. So 1 watt is how much? 1 watt is the power of an agent which does work at the rate of 1 joule per second. So time will be mentioned there, means how much time you have needed to do that work. Okay. So we can also say that power is 1 watt when the rate of the consumption of energy is 1 joule. So 1 watt equal to 1 joule per second. The power of an agent may vary with the time. So average power means what? This is also one definition of average power. This is very important. So average power we obtain by dividing the total energy consumed by the total time taken. Okay, means total joule, how much will be divided by total second. That will be the average power. Now the last is what? How we use the energy. Now let's see the commercial unit of the energy. The unit joule is too small and hence is inconvenient to express the large quantities of energy. So we use a bigger unit called the kilowatt hour. Okay. So here what will happen? In power we have got what? That it is joule per second. But now this is a very bigger unit. And these are used where actually these are used in industries. Okay, this unit is used in the industries. If we have a machine that uses 1000 joule of energy every second, then if this machine is used continuously for 1 hour, it will consume 1 kilowatt hour of energy, and this 1 kilowatt hour is the energy used in 1 hour at the rate of 1000 joule per second. See, 1 joule per second we have studied. Now here we have got kilowatt means what? 1 joule per second. Okay, so 1 kilowatt hour equal to 1 kilowatt into 1 hour. 1 kilowatt means what? 1000 watt. 1 hour means 3600 second. So how much we have got? 36 into 10 to the power 6 joule. Okay, so electrical unit energy used during a month. Electrical energy, how much you use in a month. This is expressed in terms of the units, and 1 unit means what? 1 kilowatt hour. Okay, so this is a commercial unit of energy. Clear, students? So this is the end of this chapter. This chapter is finished with the idea of part 1 and part 2. I have divided this chapter into 2 parts. It is in the playlist, students. And foremostly what we have talked about work, we have talked about energy, kinetic energy, potential energy, rate of doing work, and commercial unit of energy. And also, sorry, I have missed one thing, law of conservation of energy also we have talked about. So this is end of this chapter. Thank you. Hope you have liked this chapter. Thank you. Take care. Bye-bye.